Hello everyone, I'm Suhasini. Welcome back to my channel Learn with Suhasini Shinde. In the very last class, we have discussed about the equipotential surfaces. Then we have looked into the properties of the equipotential surfaces. Then we have derived the expression for the electric potential and the electric field. That was the relation between E and V, right? In this particular class, we'll be dealing with the electrostatic potential energy of a system consisting of two charges, right? First, let us understand what do you mean by system. When you say system, right, system is a region where only the internal parameters are considered, right? Any other thing that is outside the system is not considering into this particular system, right? Any amount or any amount of the charges or any body that is present outside the system will not contribute for any changes or any differences that is made in the system, right? For example, say there are 2 points, say A and B, right? Say for example, consider there are three charges Q1 at point A, Q2 and you have Q3, right? The influence of Q1 on Q2 and Q2 and on Q1 can only be considered in this particular system, right? Any charge that is present outside the system is not taken into consideration, right? A system is a specific region in which the internal elements are only considered. Any element that is present outside is not considered at all. That particular region is called as system, right? Now you understood what system is, right? Next is, okay, you know now what system is. Now let us understand what potential energy is. If at all you can remember, in the very last classes I told you how do you define potential energy. Any energy or the work done in bringing a charge from a region of infinite to a region of the electric field against it is called as work done, or it is stored. That particular work done is stored in terms of potential energy of that particular body, right? Say for example, what you say, you have a charge, right, that is placed in infinite distance. What do you mean? Why do I say infinite distance? Infinite distance doesn't mean that the position or the placement of the charge is so long, right? It only means that a region where no energy exists, no energy will be acting on that particular point or that particular charge. There will be no energies at all that is acting, and hence electric field at that particular region remains zero, and hence that particular region is called as infinite region, right? If at all you are bringing a positive charge or any charge from a region of infinite to the electric field or in the electric field against it, then it is some work has to be done in bringing that particular charge. Then what is that work done? That work done is stored in terms or in the form of the potential energy by that particular charge. Is that clear? It is nothing but whenever there is work done, there exists potential energy. If there is no work done, then the potential energy will be equal to zero. Is this clear? Right. Now what you do is, you have a system, okay? Now consider this particular region as a system, right? Now this system consists of two charges here, right? What we are doing here is, we want to, when I say charges that are present here, then it holds some energy, right? Any body or any charge hold at some particular region consisting of some potential energy into it, right? On the similar lines, when two charges are kept into this particular region, this becomes a system of two charges, right, which consist of the potential energy into it. Now how do you calculate what is the potential energy of this particular system? Then you have to calculate what is the potential energy of the charge 1, then addition of what is the potential energy of the charge 2, right? Then it becomes the addition of both the energies, potential energy of this particular region becomes the total energy of this particular system. Do you agree? Right? Now, when I say there are two charges, initially there is no charge, right? The system is empty, right? What is the energy that is acting in this particular system? There is no energy, and hence there is no electric field, and all the energies in this particular system is zero. Consider, right? Now we wanted, what we are finding out? We are finding out electrostatic potential energy of a system of a two charges. We are finding out what is the energy, that is potential energy of this particular system when two charges are placed in this region, right? Now initially this region is empty. First we will take one charge. We are not bringing both the charges at a time and placing here, right? First we will bring one charge, place here, then again go back, bring another charge and place here, right? Now initially it is 0, right? No electric field and no energy is present in this particular system, right? Now what you do, you bring a charge from a region of infinite. What does infinite means? From a region where electric field is 0 to this particular region, right? Say for example, you have brought this charge Q1, right? Now what is the work done in bringing the charge from the infinite region to the system? What is the work done? It is 0, right? When you are bringing a charge in no energy region, then the work done in moving any of the charge in any of the places will be equal to 0, right? And hence in moving a charge Q1 from a region of infinite to this particular space will be equal to 0, right? Now when I have placed this charge in this particular region, I said you, whenever there is a charge, it exists or it confirms an electric field around it, right? Now this charge will have electric field lines around it, right? Initially the space has no energy, now it has electric field lines into it, right? Okay, what you do next is you get another charge from a region of infinite to this particular system, right? Now you bring that point or that particular point charge and place here, that is Q2. Now do you think the work done will be 0? No. Why? Because it already has some electric field, right? And you are bringing a charge against that electric field, then there should be some work done, right? So what will be the work done in bringing the charge from a region of infinite to this particular region? That will be some work done. That work done is stored in a form of potential energy in this particular charge. Do you understand? Now you please make a note. Work done in bringing, that is W1, in bringing a charge Q1 from a distance of infinite to this region will be equal to 0. Why? Because initially there were no energy, there were no field, there was nothing. It was an empty space, and hence you can move any point into the empty space, the work done will always be equal to 0, right? Now next, another charge that is brought again from the infinity, placed at this particular point, some work has to be done now. Why the work has to be done? Why? Because the charge 1 has already created the electric field lines into this particular system, and that movement of the charge or the work done in bringing Q2 from the infinity to this particular region against the electric field some work has to be done over there. Okay, now what is the distance between this Q1 and Q2? It is D, right? Now there are two charges placed into a system whose distance is D, right? And now we have to find out what is the total potential energy of this particular system due to the placement of two charges, right? Now the energy is given by the symbol that is capital U. Right? Now what is this potential energy again? Potential energy is nothing but work done again, right? Wherever work done takes place, that work done energy is converted into the potential energy of that particular body. Initially there was no work done in bringing the charge Q1, and hence there was no potential energy. In bringing the charge Q2, you have to move against the electric field, and hence it has some potential energy. What type of potential energy it has? It is V is equal to W divided by Q. How do you define potential energy? Potential energy is defined as bringing or work done in bringing a positive charge from the region of infinity to the electric field against it constitutes some potential energy, right? In the first case, there was no work done, and hence V is equal to work done was 0 by Q, and hence V was also equal to 0, and work done was also equal to 0 for charge 1. But for the charge 2, the potential energy for that particular charge will be equal to work done in bringing that particular charge from the infinite region to this particular system will be equal to V is equal to W by Q, right? And this can be further written, W is equal to V into Q. What is this Q? Which charge it is? It is Q2. Followed, right? Next, you have this W is equal to V into Q2. What is this V? It is again a potential difference. Potential difference of what point? Potential difference at the point Q2. Why was this potential difference generated? Because of the electric field lines of Q1. So how do you define? Memorize the things from the very first class. When I started this electrostatic potential, we have derived an expression at some particular point. What is the potential energy at that point due to some point charge? Do you remember? It was V is equal to Q divided by 4 pi epsilon naught into distance d. Was this the formula that we have derived in the very last classes, the very first classes of the chapter 2? This was the formula, right? How did you get this? You can just please go through my other previous videos, then you will be understanding how did we exactly get this, right? And this can even be further written even in this manner, kq by d, right, or r, whatever distance you consider. If you consider this distance as r, then it will be r, right? If you consider it as d, then it will be d, right? Okay, now what is this potential? This is the potential at this particular point Q2 due to Q1, right? So you write it as Q1, right? So you substitute this value in this equation, we get W is equal to, instead of writing V, that is the potential difference, you write this Q1 divided by 4 pi epsilon. What is the distance between the two charges? It is d. So you write it as d. And what was the next point? It was Q2. Why it is Q1 here? Can you understand why this Q1 is written here? This Q1 represents, or it says, the potential at a point Q2. Because why was this potential? It was because of the electric field lines of Q1, and hence it is Q1, right? Now what you can write the total equation, that W is equal to Q1 Q2 divided by 4 pi epsilon naught into d. Now this is the work done, right? Work done. What this equation denotes? This is the total work done in bringing both the charges from a region of infinite and keeping or placing into this particular system. The amount of the work done that is required, or the energy that is required, is stored in terms of the potential energy of the two charges into this system. Then whatever the potential energy that is stored in these two charges will be the same potential energy of this particular system, and hence the potential energy can also be described as work done, right? What is this? This was the work done in bringing the two charges from the region of infinity to this system, right? Now this work done is further stored in form of energy, potential energy. Then hence we can write W will be equal to capital U, right? Can you understand why is this? Any amount of the work done is stored in term of potential energy, and hence whatever potential energy value will be the work done value, and whatever the work done value will be the potential energy value, and hence we equate it, that is work done will be equal to potential energy. Now this is the potential energy Q1 Q2 divided by 4 pi epsilon naught d. This is the total electrostatic potential energy of this particular system when two charges are placed into this region. Did you understand? Why is it electrostatic potential energy? Why electrostatic? Why? Because the charges are fixed at particular point. They are not moving, right? And hence the charges are fixed. It is called as electrostatic. Electro means charge. Static means not moving, right? The potential energy developed by the fixed charges into a system give rise to electrostatic potential energy of a system due to two charges. Is this clear? Right? Okay. Just now we have seen a system had two charges, then we have calculated what was the potential energy of that particular system, right? Now what if the system has three charges into it? Then how do you calculate what is the potential energy of that particular system? Let us see now, right? Now this is a system, right? In this system there are three charges at a point A, B and C, right? You have a charge Q1 at point A. At Q2 you have at B you have charge Q2, at C point you have distance between Q1 and Q2 is D1, Q2 and Q3 is D2, and Q3 and Q1 is D3. Right? Now what is the total amount or the potential energy of this particular system? What is the potential energy of the system? Whatever the potential energy of these charges are present in this region is exactly the same potential energy as of that particular system. Right? Now what we do is we will calculate one by one due to two charges, then we will ignore the third one, right? Then we will write down all the three different types of the energies, that is potential energies. How do we do is, the very previously what I have taught you in the very last minute, that was because of the two charges, right? Electrostatic potential energy of a system having two charges. Now it is three charges. When it was two charges, what was the notations or the determination? It was like we had only two charges, Q1 and Q2. You neglect all these things. You had only two charges, Q1 and Q2, separated with some distance. What was the potential energy for this particular thing? Neglecting Q3, just understand a system has only Q1 and Q2 with separation of D1. Then you call it as potential energy, that was U1. Q1 Q2 divided by 4 pi epsilon naught. What is the distance? It was D1. Right? Was this the potential energy that we have seen just now between only the two charges, neglecting all the things, right? Now what you do, you neglect these two charges, you neglect this charge, then consider only this two, right? How do you write? U2 is equal to, that is Q2 Q3 divided by 4 pi epsilon. What is the distance? It is D2. You are understanding? We are just making the things easier by comparing it to the very previous explanation. We are just considering two charges at a time, neglecting the third one, right? Now, you consider only Q3 and Q1 exist and there is no Q2 at all. Then how do you write what is the potential energy between these two? It can be written as U3 is equal to, that is Q1 Q3 divided by 4 pi epsilon naught. What is the distance? That was D3. Right? Now these are the potential energies into this particular system only when two charges are taken one at a time, right? Neglecting the third one. When you consider Q1 and Q2, you neglect Q3, you get this potential energy. When you consider Q2 and Q3, neglect Q1, you get this potential energy, right? When you neglect Q2, you consider only Q1 and Q3, you get this potential energy, right? Now what is this energy? What do you think? Is it the scalar or vector? When we say energy, right, we do not tell in terms of direction, right? Energy has only magnitude, right? Say for example, my energy is some kilocalories, right? I cannot say some kilocalories down, up, or right or left, right? It has no direction, right? Energy has no direction. It has only magnitude. When I say kilocalories, then it is only a magnitude, right? And hence, in the same lines, energy, that is potential energy, is not a vector quantity. It is scalar quantity. A quantity which has only magnitude but no direction for itself is called as scalar quantity, right? Now you have three scalar quantities, that is the scalar quantities in terms of three parameters, that is U1, U2 and U3. Now you have three things into one particular system, then when you add a algebraic sum of all the parameters will definitely give you the total potential energy of this particular system. Do you agree this, right? So what you do, if at all you want to find out what is the total energy of this particular system, then what you do, the total energy of the system can be given as U1 plus U2 plus U3. Right? There are only three charges, so it is U1, U2 and U3, right? Substitute the values. U is equal to, what was U1? Q1, Q2 divided by 4 pi epsilon naught D1, right? Plus, what was U2? Q2, Q3, 4 pi epsilon naught D2, right? Plus Q1, Q3 divided by 4 pi epsilon naught D3, right? These were the individual potential energies of the system. When you add the algebraic sum of all the energies will give you the total energy of this particular system, right? So what is common into these terms that you can write outside? 1 divided by 4 pi epsilon naught is common. Then Q1 Q2 divided by D1, Q2 Q3 divided by D2 plus Q1 Q3 divided by D3, right? Summarizing it, we can write a final equation or a standard equation. 1 divided by 4 pi epsilon, right? Summation of all the quantities, right? I is not equal to J, right? Qi Qj divided by Dij. What does this mean? What does this equation mean? This equation is the total amount of the electrostatic potential of this system when it has 3 charges into it, right? It is 1 by 4 pi epsilon is taken common. Why? Because it has all the terms here. It is taken common. Summation of Qi. We are taking, when I say system, there are always minimum amount of the charges the system holds. It is 2, right? So there are 2 different charges into it, Qi and Qj, right? Now this is Dij. What is Qi? If at all it is 1, it is 2, then it is 1 and 2, the distance between 1 and 2. If I and j value is 2 and 3, say for Q2 and Q3 charge, then the distance between 2 and 3, right? It is written like this. Why I have written I is not equal to j? It cannot be equal to j, right? When I will be equal to j, then the system has only one charge which has no value. You cannot call that as a system, right? So if at all I is 1, j cannot be 1. We are finding out the energies due to minimum of 2 charges into a system. So I cannot be j. If at all I is 1, then j should be 2. The second another charge, right? And hence this is the total amount of the electrostatic potential energy of the particular system when it has 3 charges into it. Is this clear up to this point? Till now what we have considered, we had a system. Initially it had no energy or electric field into it. The system was 0, right? And any point that is coming from the point of infinity, then it had placed into the system, then it had created electric field and so on, right? Now what if this system already consists of some electric field lines and then you are getting 2 points into it, then what is the potential energy of that particular system is found out here, right? You make a difference, you make a note here, right? Earlier what we have done for the 2 charge system and the 3 charge system, initially a system was vacant, right? It was free space. There was no energy acting into it and hence the electric field was equal to 0 whenever you bring 2 charges or either you have brought 3 charges into a system. But now at this point you have a system where it has already electric field present, then now you are getting 2 charges into that particular system and you are finding out what is the electrostatic potential energy of that particular system. Is that clear what the difference is, right? Now say for example you have a system, right, and you have already electric field lines present here, right? Now you get 2 charges. Say for example you get charge Q1 at this point A from a distance of infinite, right? This has already electric field in this direction. The electric field considered here is uniform in nature. Uniform means the magnitude and the direction of the electric field at any region or at any point in this space will be equal, right? It will be constant, right? Now that particular field is called as uniform electric field, right? Now what you do is this is a space or a system which has already uniform electric field acting into it. We get a charge from a distance of infinite. What does this mean? From the distance of infinite, it means from a distance or from a place where electric field was 0, right? From that particular distance, that is from infinite, and we keep here at a point A, right? Due to this electric field at this particular point, right? Now this charge is brought against the electric field, then there should be some work done. Whenever I say there is work done, there is definitely a potential. Now you have a potential of V1 at a point Q1, right? Now you bring another charge from a distance of infinity at this particular point B and place here, right? You get a point charge from a distance of infinity at a point B. Now the distance between the 2 points will be equal to D, say for example, right? Now initially there was only electric field lines and we have got a charge Q1 from infinity to this point, and hence it had to overcome only one electric field, that was this electric field, and hence its potential was Q1 and V1. Right, that is V1, right? Now the second charge, when we were bringing that charge from a region of infinite to this particular point B, you have to overcome two electric fields, right? You have to overcome two potential energies, one because of this electric field and another because of the region that is being created by this Q1. When you place a charge Q1, it has some electric field lines around it, right? And when this charge has to come, there are two electric field exist. One because of the charge that already have it, that holds electric field, uniform electric field, and another electric field is because of this particular charge Q1, right? Now what is the work done, or what is the potential? Now just now we have seen, right? What is the potential at this point, that is V1? It will be work done in bringing a charge, say Q1, right? How can this work done? What will be the work done? Work done will be equal to V1 Q1, right? Now this is the work done that is required in bringing a charge from the region of infinity to a region of electric field, right? In the similar manner, now there exists two electric field, one because of this uniform electric field and also because of the charge that is electric field lines because of the charge Q1. So there act two electric fields on this Q2, right? Now what is the work done in bringing this charge from here to here? Then what is it? It is again, what is the potential energy that is at this particular point? It is V2, right? What is the potential energy at this point? V2. It is work done in bringing a charge Q2, right? Now work done can be written as V2 Q2, right? Now this is the potential, or this is the work done in bringing a charge against electric field. But you have another electric field due to this Q1. You also hold some potential energy against this one, right? So how do you write? I have said you at any particular point what will be the potential energy. We have seen in the very last classes it was K Q1 Q2 divided by D. Why I have written Q1 Q2? In some terms, in some areas we write only Q1. Why? Because the other one we will take at unit positive charge, right? So it will be only 1. That will be considered as 1. Now here we have two different charges. So we mention it as V is equal to K Q1 Q2 divided by D. Potential energy is nothing by the work done, right? Work done is stored in terms of potential energy. And hence what is the work done in bringing the second charge? That is because of electric field and because of charge Q1, right? The total work done, that is W2, will be equal to, this is W1 and this is W2, will be equal to V2 Q2 plus K Q1 Q2 divided by distance between both the charges, right? Now what is the total potential energy? Now you sum it off. The algebraic sum of the work done of Q1 and Q2 will be equal to the potential energy of that particular system which has electric field into it, right? How do you write now? The total work done will be equal to W1 plus W2. What was W1? W1 was V1 Q1 plus what was W2? It was here. What was W2? It is here. That is V2 Q2 plus K Q1 Q2 divided by D. Now this is the total work done in bringing the two charges from a region of infinite to a region or to a system which has already electric field into it. Did you follow up to this point, right? Now what is this W? Now this work done of this system is stored in terms of potential energy, and hence we call work done will be equal to potential energy U, and hence U can be written as V1 Q1 plus V2 Q2 plus K Q1 Q2 divided by D. This is the potential energy expression for a system consisting of electric field into it. Did you follow these things, right? The very two expressions that we have derived very previous for this, where you had a system with no electric field. There was no electric field. The system was empty. First you introduced two charges, then in the very second derivation you introduce three charges, right? But here what is the difference? A system has already electric field into it, right? And hence when you introduce the two different charges into this particular system, then what is the total amount of the potential energy that is generated here is calculated in this derivation. This was all about today's class. In the very next class, we'll be learning what is the potential energy when electric dipole is placed into an electric field, right? Then hopefully I have explained everything very properly, which is reaching very proper at your end, right? And you please do subscribe to my channel and share the link with your family and friends, right? If at all any suggestion, please drop down into a comment box. Then you can also get a material for this particular topic, that is electrostatic potential and capacitance, in the description box. You just go there, visit my website, download the notes, and it will become very easy for you people to understand the things better, right? Now this particular video covers three different topics: electrostatic potential due to two charges, due to three charges, and also a system where it has electric field already into it, right? And thank you so much.